In this section, section P5, we'll look at a lot to do with lines. So amongst those, we'll talk about the slope of a line. And similar to the last section, we'll talk about the x and y intercept for a line, and we'll do that both graphically and algebraically. And then we'll talk about pairs of lines and whether or not they are parallel or perpendicular, and how to tell algebraically if this is the case. Okay, so our first example, we'll look at the slope of a line and what this concept is. So first thing, let's just draw a line, and I'm going to make a nice big set of coordinate axes here. And then let's say that our line goes between, say, this point down here at -1 and this point over here at 1. We'll just use this one as a quick example. So I want the line to go between those, and so something about like that. Okay, so the slope of a line is defined, as you may recall, as rise divided by run, okay, or sometimes delta y over delta x. And then the symbol that we typically use just for slope, because slope totally has the letter m in it, is m. Okay, so what is the rise and run in delta y, delta x? Well, if we look at our line and we pick 2 points, so as we did here, I picked this point and this point, and what we want to do is look at how far up did I go from this point as I moved to this point, and that number could be negative, meaning I went down, and how far to the right did I go. Now in this simple example, the numbers are going to be really, really easy. So delta y is the y coordinate at this point is 0, and the y coordinate at that point is -1. So 0 minus -1 is 1. And that makes sense. We went 1 unit up. Similarly, delta x, we end at the x-coordinate 1. We started at the x-coordinate 0, and so that's also 1. So in this example, our slope is 1 divided by 1, which is 1. Now, as I said, the slope could be negative, so let's look at another example, another line. So let's put this point up here at, say, 1, and then draw the line through here. So our red line has delta y. In this case, we end at the y-coordinate 0. We started at the y-coordinate 1. So end minus start is -1. And then our delta x, in this case, is the same as before. And so our slope is -1 divided by 1 is -1. Okay, now there are 2 other sort of special cases that we could consider. The first is, what about if the line has essentially no slope? So I'll draw in a horizontal line in green, and so horizontal has 0 for its slope. And the reason for that is if I pick 2 points on it, they have the same y-coordinate. and so delta y would be 0, and hence m is 0 divided by something, and that's always going to be 0. Okay, so horizontal lines have 0 slope. The other special case is vertical lines. And a vertical line has sort of the opposite problem. If I pick 2 points on it, they have different y coordinates, so delta y is not going to be 0, but delta x is 0 because they both have the same x coordinate. And that's a problem because then we'll have m being something divided by 0, and division by 0 is not permitted. Okay? So in this case, we say that the slope is undefined, or simply no slope. Next, we'll look at algebraically how we write down slope. So in the last segment, we saw how to calculate the slope if you had an actual line in the plane. Algebraically, though, we don't want to always have to graph everything just to figure it out. So the most common form that you'll see the equation of a line is in what's called slope-intercept form, or you may have heard of it as y equals mx plus b form, because that's exactly how it's going to look. So the equation will be in this form, and m is, as before, the slope of the line, and b is the y-intercept. Okay, so for example, if we had the line y equals 2x plus 1, then the slope in this case is 2, the coefficient of the x, and the y-intercept is 1. Okay, so let's just graph this line real quick to get a sense of where everything is. So we'll have a set of coordinate axes, and when you have something in slope-intercept form, it's very easy to graph it. The first thing is, let's put a point where our y-intercept is, and that's at 1. So I'll just put a point here, 1 unit up. And then we need to look at the slope. So remember what slope means. It means rise over run. So rise over run needs to be 2. So for every unit to the right we go, for every 1 unit we run, we rise 2. And so if I move 1 unit to the right, I need to go 2 up, and that gets me a second point on this line. And then, once I've got 2 points, that's enough to draw a line connecting them, and there's our line. Now, you may recall in the last video, in section P4, we also talked about intercepts. We talked about both x and y intercepts. So let's look at those here for this equation and see why it makes sense that b is the intercept. So remember, the y-intercept, the y-intercept happened whenever x equaled 0. Okay? So if we take a line in the form mx plus b, and we set equal to 0, x equal to 0, what do we get? We get y equals m times 0 plus b. M times 0 is just 0. And so, and that's regardless of what the number m is, and so we get y equals b. And this shows us that what we said was the y-intercept is actually the y-intercept. So that just puts all of this on firm footing. We could also find the x-intercepts. The x-intercepts aren't apparent from the form of the line. We actually have to do a little bit of algebra. So to find the x-intercepts, we set y equal to 0. And so let's just do that here. So for those we get, if y is 0, 0 equals mx plus b. And so we need to move the b over and then divide by m. So the x-intercept occurs at the point negative b over m, and that of course requires that m is non-zero, because otherwise we divide by 0. So let's go back to the red line for a second and let's calculate what its x-intercept is. Now graphically we can easily see that it's right here. But where is this point? What are its coordinates? So let's calculate that real quick. For us, in that example, the slope was 2 and the y-intercept was 1. So x should be here, negative b, b was 1, and the slope, m, was 2. And so we get that the x-intercept in this case is negative 1/2. And this is why it's important to determine these things algebraically if you can, rather than relying on the graph, because looking at my graph, we might have guessed that this point was at x equals negative 1, when in fact it's supposed to be at x equals negative 1/2. So if you try and use a graph to make or to determine the intercepts, you have to make sure that the scale is absolutely perfect, or else you'll make silly mistakes. Okay, in this segment we'll look at how you tell whether or not two lines are parallel versus perpendicular. Okay, so the first thing we need is just a quick set of coordinate axes, and actually these provide sort of our first example of perpendicular lines, because the coordinate axes we always set up perpendicular, and perpendicular is to mean that they meet at right angles, just like in geometry. Okay, now parallel lines, and this is one really nice thing about the word parallel, it actually has an example of parallel in it. So the double L right there, those L's are parallel, and in the same way, if I draw two lines like so, those are parallel. So if we look at our parallel lines here, the red ones, we can probably guess something about algebraically what needs to be true. So parallel lines let's clean that up a little bit. Parallel lines have the same slope. Okay, and so an example algebraically would be something like this. If the first line has equation y equals mx plus, say, b1, then the second line needs to have equation y equals mx plus b2. But the m's, slopes, are the same. Okay, so same slope. Okay, so in the last slide or segment we looked at the equation y equals 2x plus 1. And so let's come up with another line which is parallel to this one. We need to keep the same slope, but we can pick any y-intercept that we want. So how about just something ridiculous, 1832. So these two lines have the same slope, different y-intercepts, but that's okay. All they have to have are the same slopes. Okay, so now let's look at perpendicular lines. So perpendicular lines, and for this we won't look at the x and y axis example immediately. So let's just take two lines, y equals m1x plus b1, and line 2 we'll call the line y equals m2x plus b2. Okay, so we've got two different lines. They conceivably have different slopes, m1 and m2, but they might be the same by dumb luck. And they conceivably have different y-intercepts, b1 and b2. So L1 is perpendicular to L2 if and only if the slopes multiply to give the number -1. Now another way to say that is if m1 is 1 over m2 negative. Okay, so the negative reciprocal. Okay, and sometimes we just notate this for convenience. L1 is perpendicular to L2. And then sometimes, because mathematicians are lazy, the phrase if and only if will abbreviate like this. So if with two F's means if and only if. Okay, so we've learned here parallel lines have the same slope and perpendicular lines have slopes which multiply to -1, or one slope is the negative reciprocal of the other slope. So next let's look at two quick examples. Okay, so for our first example, we'll look at example 1. Let's say that we have the lines y equals 5x minus 1. We'll call this line 1. And then we also have line 2, which has the equation y equals 5x plus 6. And we're asked to determine whether or not these lines are parallel, perpendicular, or neither parallel or perpendicular. So in this case, the first thing we should look at is, are they parallel? That's the easiest to identify. So let's look at the slopes. 5 for this one, and lo and behold, 5 for that one. So these lines has the same slope as L2, and hence they are parallel. Okay, and we can notate that L1 parallel L2. Okay, and so next let's look at another example. This time we also have two pairs of lines, L1 and L2. But this time the equations for them are L1 is y equals -4/3 x minus 2, and y equals 3/4 x plus 1, and that's L2. Okay, so the first thing, again, let's look at the slopes. The first one has slope negative 4/3, negative 4/3, and the second one has slope 3/4. Those are definitely not the same number, so these are definite not parallel. But they might be perpendicular. And to do that, we just need to check what is the product of these slopes, or what would happen if we put a negative in front of one of them and flipped it over. So either way. So let's just multiply the two. Negative 4/3 is the first slope, and if I multiply that by 3/4, I get negative 12 over 12, and that of course is just negative 1. So these slopes multiply to be negative 1, and so these lines are perpendicular. And that's it.